Good morning, students. Our today's topic is electrostatic potential due to a point charge. Students, as in the previous topic, we define the electrostatic potential. Okay, so in order to find the potential at a particular point due to a single charge, consider a charge, say plus q, at some position. And now, if we have to calculate potential at point P, which is at a distance, say r, from the point charge Q. Now, from the definition, we know that potential is the amount of work done on a unit charge in bringing it from some point at infinity, from infinity to this point. Okay, let this is a point at infinity from the charge plus q. Now, if we consider some intermediate point, say point A, okay, which is at a distance, say x, from the charge. So now, if we place a unit charge, say 1 coulomb charge of positive at point A, so it experiences a repulsive force which is given by, say, F. Okay, so in order to counter this force, we must apply some external force in moving this charge from A to P. So we know that this force is obtained by Coulomb's law, and this force is given by F, which is equal to 1 by 4 pi epsilon naught q1, that is plus q, into q2, that is 1, q1 into 1, divide by the distance between these two is x, say x square, and the direction of this is along, as it is repulsive, so along pa produced, so along it is pa, so it is equation 1. Okay, so now if we want to bring this charge from A to point P, so we have to do some external work. Let dw is the amount of work done in bringing a charge from A to, say, nearest point B, which is at a distance dx. Okay, so the small amount of work done in bringing unit charge, unit positive charge from A to B, that is AB, which is equal to dx. Okay, so we can say dw must be equal to force into distance, as force is a vector and distance is also a vector. From the diagram it is clear the force and the displacement are opposite, so we can write it as f dx cos of 180, so we can say minus of f dx. So this is the small amount of work done. Now the total work done in bringing the charge from infinity to point P, which is at a distance of r from the point charge. Okay, so we can integrate the equation second, that is integration of dw, which is further equal to minus of integration from infinity to point r f dx. Okay, now using the value of force from equation 1, we get this work done must be equal to minus of integration from infinity to r 1 by 4 pi epsilon naught q upon x square into dx. So now integrating this equation, we get minus of taking q and 1 upon 4 pi epsilon naught common as it is constant, and we are remaining with integration infinity to r 1 by x square dx. So integrating this, we get minus q upon 4 pi epsilon naught minus of 1 by x. Limit of integration is from infinity to r. Now putting the limits, we are getting with q upon 4 pi epsilon naught minus taken out, it becomes plus. So the amount of work done, that is w, must be equal to q upon 4 pi epsilon naught into 1 by r minus 1 by infinity. Okay, and that should be equal to q upon 4 pi epsilon naught r, that is w. This work done is known as the potential of point P, so we can write it as V is equal to 1 upon 4 pi epsilon naught q upon r. Say this is equation third. Now as it is clear from the expression 3 that for a positive charge potential is positive, and for a negative charge potential is also negative. So we can write for positive charge potential is positive, and for negative charge potential is also negative. Okay, now if we put r is equal to infinity, it means at a point which is at infinity from the charge. So when r is equal to infinity, so v is equal to something upon infinity which is equal to 0. So at point infinity potential of the charge is 0. Also from this equation it is clear that for v is proportional to r, that is at a particular distance from the charge potential remains same. So we can say potential is spherically symmetrical around a charge. Okay, the next one point is, as it is clear that electric field is proportional to 1 by r square, in the previous topic we have discussed about this, and the potential is proportional to 1 by r as it is from equation third. So we can say the curve for electric potential is becomes more steeper than the curve for electric field when it is drawn with respect to the distance from the charges. So we can draw these two curve like this. On x-axis, if we take say distance, that is r, and on the y-axis we take e and v. Okay, so curve for electric field becomes like this. Okay, and for potential it becomes more flatter, that is more steeper, so we can say it looks like this. So this is the curve for v, and this is the curve for electric field. Okay, so this is all about electrostatic potential due to a point charge. Thank you very much.